Thank you to 황가운 교수님 for the kind introduction, and thank you to 임미경 교수님 for allowing me to have this opportunity. I've been here now. I arrived in the beginning of August in Daejeon, so I've been here now 4 months, and I told my wife just about a week ago that I consider it a real privilege to be able to teach the best and brightest minds in Korea here at KAIST. And I'm glad to see, I guess many of you are forced to be here anyways, but I'm glad to see that, that many of you are here. So without further ado, today's talk, let me just briefly outline. I'm just going to give you a brief historical perspective on what my topic is. Then this is the mathematically heavy part of my talk. Most talks, you know, the math gets harder as it goes along. I'm going to give you the math while I still have your attention, and then do the easy part later. And so this is just an explanation of what is a stable limit theorem. It's a generalization of the central limit theorem. And then mostly it's just going to be a story after that. I'll give you some ideas of proof, but nothing technical. There's more pictures than equations in my talk, because this, you know, one of the last colloquiums, I know that you've suffered through many, you know, slides with several equations. So if you believe the old adage that a picture is worth 1,000 words, then there are over 15,000 words in my talk. Okay, so okay, so the history here. Let me start with the central limit theorem, which everyone I think is familiar with, which is the most common case of the stable central limit theorem. And it says that if we have independent identically distributed mean zero random variables with finite variance, or equivalently finite second moments. This is the second moment, but in the case where it's mean zero, this is exactly the variance. Then it says that if we choose any x, this probability here converges to, as n goes to infinity, to the probability of the normal 0, 1 being less than x. So this is what's called the distribution function, or the CDF of the normal. So these probabilities converge, and when all these types of probabilities converge to all these types of probabilities, we call this weak convergence of the distributions, or weak convergence of the random variables. And here, notice that what I do is I sum the random variables and I divide by the standard deviation. So the variance of this sum is actually sigma squared times n. So the standard deviation here is sigma square root of n. And normally, usually we would subtract off n times the mean, but in this case, I've assumed that the mean is 0, so I don't have to subtract anything off. So this was proved in the very special case where these are IID Bernoulli's random variables, just coin flips, 1 or 0, with probability p. Okay, let me say that the first thing that was proved was when you sum IID Bernoulli's and divide by n, then this converges to the mean. This is the so-called law of large numbers. And Bernoulli proved the weak law of large numbers in 1710. This central limit theorem is really a refinement of the law of large numbers. You look at the growth rate here. This is n times this, and then now we've subtracted off the mean, and then now we look at the fluctuation around n times the mean. Okay? So this is really the first step. And it took only 23 years for de Moivre to actually prove in the same setting that the fluctuations of the binomial, the sum of these guys, is approximately normal with the correct normalization. But then it took over 100 years for them to prove that this happens more generally, not just for binomial random variables, not just for sums of IID Bernoulli's, but for sums of IID random variables where they have moments of all order, or here this is sometimes called the moment generating function, or you can also think of this as the Laplace transform, and of course this was proved by Laplace. I guess it would be the Laplace transform if you put a minus sign there, but it's essentially the same object. And he proved that when this exists, then you get convergence. So this is a universal result. It says that no matter what you start with, when you add them up, you normalize, then you converge to the normal. And Poisson objected. He said, well, the central limit theorem doesn't hold for this PDF. Okay, so this is what's called the Cauchy distribution, as many of you know. And what what's wrong with this distribution? Well, it doesn't actually have a finite second moment. It doesn't have a finite variance, so it actually doesn't satisfy the hypothesis I've written here. And so then the race was on to say, well, we found an example that doesn't work. Where's the boundary? So that's what mathematicians like. They like to say, okay, here I have some assumptions. I proved this. How much can I weaken these assumptions? And they found a counterexample. So now we know it has to be somewhere in between. And it took, again, another 110 years for Levy and Lindbergh individually, separate papers, to prove that this holds under finite second moments. And actually, Levy proved a slightly stronger. You can have infinite second moments, but as long as you have finite moments of all order right up to 2. So if you have finite 1.9999, moments, et cetera, for all epsilon less than 2. Okay, so so this is this was the state of the art essentially for the central limit theorem. Okay, so why do we need finite second moments? So now I want to tell you the generalization, and again, here this is the mathematical heavy part, but it's not so heavy. Okay, so let's just assume that we have a CDF. So this is 1 minus the CDF, 1 minus the distribution function. It's a tail of the distribution, and let's assume that it's of order 1 over x to the alpha. So then if we take the derivative of this, that's the PDF. And so the derivative is of order 1 over x to the alpha plus 1. So this is as x goes to infinity. We don't really care what happens near the origin. And then now, in order to take the second moment, we just multiply by x squared. We integrate. And here I've just integrated from 1 to infinity just to get the tail. This is the tail determines the property of whether you have the finite nth moment or pth moment. Okay, and notice that this is infinite whenever alpha is between 0 and 2. Right? This is a standard result. It's just the P series, right? So this is a situation where we have essentially, whenever alpha is between 0 and 2, we have infinite second moments. And now if we just replace x by n to the 1 over alpha, note that the alphas cancel out, so we get 1 over n here, and we just put in n to the 1 over alpha. So here, what we're saying is the probability of x being of order bigger than n to the 1 over alpha is about 1 over n. Now that's a very small probability, but if you have n of them, on average, one of them will satisfy this condition. One of them will disobey this, will have a large tail, will be of order n to the 1 over alpha. And now if you have something of order n to the 1 over alpha here, where alpha is smaller than 2, that's bigger than square root of n, right? Think alpha is equal to 1. So then it's just n over square root of n. And of course, that gets too big. And for any u, this probability is going to go to 0 because we disobey this. We diverge here. So this is now the general version. When alpha is equal to 2, we get the central limit theorem. But when alpha is less than 2, we get all sorts of different limit theorems. And these are called the stable limit theorems. These are called the alpha stable limit theorems. For each alpha less than 2, we have a whole lot of different limit theorems. In fact, there's not a single one. There's many, many. Okay? And so these converge to different so-called stable laws when you sum them and you divide by n to the 1 over alpha. So hopefully that makes sense to everyone. And now let me show you why, a little bit why. Well, you kind of already can see that this is of order n to the 1 over alpha, but only one of them, only one on average, or a finite number of them on average, satisfy this. So why should this occur? Well, the key to that is really in that second, this second bullet point, this blue equation, or this blue asymptotic. And now what I'm going to use is I'm just going to divide by n to the 1 over alpha on both sides. So now this divided by n to the 1 over alpha bigger than some constant c is of order 1 over n. And many of you know Poisson convergence. If we have something of probability 1 over n, and we have a lot of independent copies of them, if we have n independent copies of them, then a Poisson number of them occur. So Poisson number of times this occurs because we have 1 over n, or in general lambda over n, and the opposite occurs. So we just put a 1 whenever it occurs and a 0 whenever it doesn't occur. And this is a Poisson number of guys. So the sum of the number of times that this occurs is Poisson lambda. And now that should kind of convince you maybe more that this happens. But what about all the other terms that when it doesn't happen? Those can actually cause divergence. So we have to do a little bit more argumentation. And then we use for that we use the Poisson, the compound Poisson, which says that, so now if this is of order lambda over n, then the probability that this lands in any interval, so think of, originally we said from constant c to infinity, but now I just take any interval, take any small interval, and the probability that it lands in that, one can easily deduce from this that the probability that it lands in some interval is also of general order 1 over n. Okay? This is something that you can calculate. It's not too hard, but I'm not going to do it, but let's just assume this to be true. And then a general result, now what we can take the guys above c, we have a Poisson number that are bigger than, divided by n to the 1 over alpha are bigger than c. And then for all intervals below c, we just kind of divide them up, and they're a Poisson number that are that land in each of those intervals. And we can kind of take those intervals down to 0, and we can kind of eventually eat up this whole sum. So what we have is a bunch of sums of a bunch of Poisson random variables, essentially. Okay? So that's kind of what that's the story here, is that through this idea of compound Poisson convergence, you get a bunch of Poisson random variables that are, this is essentially a sum of a bunch of Poisson random variables. Or if you want, this is essentially a compound Poisson random variable. So let me show you a picture of what a compound Poisson random variable is. So here, this is just a typical Poisson process. A Poisson process is whenever an event occurs, you jump up by 1. So you can think that we divided this up into a lot of individual times, and the probability that an event occurs at any individual time is 1 over n. And then in the end, when you count the number of occurrences, you get this interval here is Poisson distributed. Okay, so just think of time 1, there's Poisson, this is a Poisson point process. But now, there's no reason to just count the events. Why don't we look at this and think of this as jumps of size 1? And why should we always jump by size 1? We can jump by other sizes. So here you can see this is a big jump, but then we have a bunch of small jumps in between, right? So we can vary the jumps. And that's exactly what I did before. I looked at when it landed above C, but I also looked at landed when between A and B, and I can kind of think of A and put some point in between A and B and kind of approximate and just say, now the jumps are of size A plus B over 2, right? On the average for each of those intervals. And there's no reason that we should restrict ourselves to just positive jumps. Why not have negative jumps too now, right? So the interval AB could be on the negative axis. And this is what's called a compound Poisson process. Essentially what happens is each time you have actually the times between each of these jumps is actually an exponential random variable, as many of you know. And each time something arrives, you jump according to some random distribution, and that's the compound part. So there's a random jump distribution. Okay? So now this is the next slide is the most technically heavy part, and I promise it's all downhill from there. So just stick with me for 2 more minutes, okay? Okay, so now if we have a constant times a Poisson random variable, then as many of you know, some of you are in my graduate probability class, and as many of you know, the distribution of a random variable is completely determined by its characteristic function, the Fourier transform of its measure. So if I look at the characteristic function, this is just the Fourier transform of its measure, integral of this guy d mu with respect to some probability measure, then the Fourier transform turns out to be this guy right here, where lambda is just the parameter of the Poisson random variable. And C is the jump size. Okay? So C is the jump size, or C is in fact just the constant that we multiply times the Poisson random variable. So each time we jump up C instead of jump up 1. Right? So this is just a single constant times a Poisson. But now if I have a bunch of Poissons, it turns out there's something called thinning of Poisson processes that says that if we jump of different sizes, the lands in each of those jumps are actually occur independently. So in other words, if you look at kind of think of you're owning a store and people coming in as customers, they come in at exponential time, so you have a Poisson number of customers. But if you count the women and the men, then you can think of those as 2 independent processes, right? And maybe the women spend more, so you multiply them by C equals 10. And then for the men, you multiply them by 0.5, whatever. So that's the idea. And so each of these intervals corresponds to independent Poisson guys, and you just essentially sum them up. And in the end, you essentially you get this guy as your characteristic function, which is just this. This is just all I've done is replace c by ck, and then instead of having a delta mass just at ck, instead of requiring only ck jumps, I can have a delta mass at ck, a delta mass at a different type of jump, a delta mass at a different type of jump, and then I average the delta masses, and then I get a probability measure here. Okay? And then this is lambda times the probability measure. So lambda is the rate of the Poisson process. So if lambda is high, then you actually have a bunch of customers coming in. You have a bunch of jumps. If lambda is low, then you have less customers. And so this measure here determines how many arrivals or how many customers you have or how many jumps you have. Okay? And so now, so this is probably the part that I'm going to just skim over. So the problem is that actually, for stable laws that I've shown you before, it turns out that the measure here is not finite. It's not even a probability measure. So here, this is a probability measure times lambda, so this is required to be finite. But for stable laws, what happens is we actually have infinite measures here. So we integrate now with respect to an infinite measure. And in order to compensate for that, because this sort of, what happens is as you get smaller and smaller and smaller jumps, you take the probability measure, and the probability measure, the measure nu times lambda, d nu times lambda, can have a singularity at 0. So the measure gets bigger and bigger and bigger. And you can have a singularity at 0. But now think of that, what that says, that you have many, many more jumps, but they're all getting smaller and smaller and smaller. Okay? So above any jump size, you only have a finite Poisson number of jumps, but as you go towards 0, you can add more and more jumps, and you can add actually an infinite number if they're getting small enough fast enough. But sometimes they don't get small enough fast enough, so what you do is you just use this trick where you kind of notice that this -1 is the first term of the power series expansion of this guy, and if you think that at near 0 this is just 0, then this is the second term of the power series expansion. And actually, if you pull this out, if you integrate this d nu, then this is just a constant. So what we're doing is we kind of compensate by subtracting a constant. And so we have a bunch of sums of Poisson jumps, but we subtract a constant. This is kind of canceling out and has the effect of giving us a mean 0, and in the end allowing this thing to converge. Okay, so that's, I waved my hands a little bit, but of course I can't explain the whole theorem. I'm just trying to give you the idea in a couple slides. Okay, so that's what a stable law is, and in fact this is the characteristic function of a stable law when d nu is exactly this for alpha less than 2, from between 0 and 2. And actually here I've integrated from 0 to infinity, which means that I only initially have positive jump sizes, but in general you could have positive or negative jump sizes. And here, one last thing I should point out is this doesn't mean actually that the random variable is positive because I'm summing up positive jumps, because here this thing that I've compensated means that I've subtracted a constant, so sometimes I can actually go negative, okay? Because I'm continually subtracting a constant. So actually what it turns out to be in the end is you're kind of subtracting a line, okay? So that's stable limit theorems in a nutshell. All right, so again, that's the mathematically heavy part. Let me show you now what happens. Well, here's a two-dimensional Brownian motion. Now, if you do this in the plane, so I described one-dimensional process, but you can imagine that you can extend this to a two-dimensional process, and if you do that, then you're adding a bunch of jumps. Okay, so the jumps above a certain size, they're only a finite number, but notice that there are many, many small jumps, and you can't actually see all the jumps that are going down to 0. Okay, and actually this process, if you look in time when it's jumping, it's Cantor-like. Okay, so it's jumping all the time. It's jumping all the time. So at this time it jumps to here, and this is taken from a paper in Nature where they were showing that where these physicists, I guess, had constructed some material where they were able to get light waves to behave more like Levy's stable motion than Brownian motion. And Levy's stable motion is the alpha generalization for Brownian motion when alpha is less than 2. So when alpha is equal to 2, you get Brownian motion. When alpha is less than 2, you get so-called stable motion. Okay, so now let me give you a real-life example. Okay, so this is called the on-off internet traffic model. And so you have a bunch of workstations, and then when the workstation is on, maybe you think they're constantly using the internet, so they're downloading something or they're on the internet. And so you have a rate 1 of being on, so internet traffic. And then when the person leaves work or when they're, whatever, take a bathroom break or something, then it's off, and so you have a constant rate of 0 of use. And it's known that actually, so what you do is you just have it on for tau 1 time, off for tau 2 time, on for tau 3 time. So all the odd number times are on, all the even number times are off. And it's known that actually these taus, the data shows that they behave like this, which was exactly the tail condition we had in the case when alpha is between 1 and 2 in the previous slide. So if we sum up the times that you're using this computer and we properly normalize, then this should converge to a stable law. In fact, so if you sum this up, you subtract the mean, and you divide by n to the 1 over alpha, then this converges to a stable law. Now, let me point out that it's important that alpha is bigger than 1 here, because when alpha actually gets too small, you actually don't even have a finite mean. Okay, so remember, when alpha gets below 2, you have no finite variance, but when alpha gets below 1, you have no finite mean. Okay, so alpha equal 1 is a Cauchy distribution where you have all moments right up to the finite mean, but it has actually infinite mean. Okay, so this is the model. And so here's a picture of the model. So here, these are the seconds if you want, and then it's on, off, on, and here's another user, off, on, off. And these times have heavy tails. The probability that you're on for n to the is of order n to the 1 over alpha seconds, if you want to say. Okay? And actually, this is the data, and it's from Sid Resnick, 2011. So those of you in my probability class, you know we're using Resnick's book. So this is from one of his papers with a graduate student of his. And he looks at the times of people in the Cornell computer labs, and they're using TCP and UDP protocols. So this is the UDP protocol, TCP protocol. I don't even know what those means, but it was in his paper, and this is the data. And you can see if you do a QQ plot against a normal, in the middle it's okay, but at the tails, it just goes off the charts. And it signifies that it has heavy tails. Okay? And so this model is backed up by the data. All right? And so this sort of stable law behavior, this sort of heavy tail behavior actually exists in the real world. Another place we see this oftentimes is financial data. I don't have, well, okay, so I don't have any pictures of that, but I think there are people here that maybe know finance better than me, so I'll let them talk about that at a future date. Okay, all right, so now let me shift gears. So that's heavy tail distributions and the processes that are related to them, which are the alpha stable Levy processes. And now let me shift gears and say I'm going to apply this to a setting of physics. And in the setting of physics that I want to apply to is statistical mechanics. Okay, so statistical mechanics tells us that it's impossible. Well, okay, so what we know from physics in general is that it's impossible to know for many, many particles their positions and all their positions and all their joint momentums or velocities. Okay? Now, we know this from quantum mechanics, but even before quantum mechanics, we knew this because we can only do this in general for 2 bodies. And if you get to 3 bodies, it's very hard. I mean, you can do special cases, but you can't solve this in general. So we can't even do this for 3, let alone many. Okay? So this is impossible to know. And then quantum mechanics came along in the early 1900s and said, actually, this is really, truly impossible. Theoretically, it's impossible to know all these, okay, at the same time, even for just one particle. Okay? So, well, that's a different story. But okay, so anyways, it's impossible to know these at the microscopic level. But what statistical mechanics does is it leverages, it takes many, many particles, it takes n to infinity, leverages laws of large numbers, and also the uncertainty caused by them to actually be able to deduce some laws of nature. Okay? And we figure out those laws of nature at a macroscopic level. And let me say that, and so I'll discuss why we're allowed to do this in a second. But let me say that sometimes we even need large numbers just to describe a certain physical concept, like pressure. Pressure, you cannot, the pressure one particle imposes on something is meaningless because it's per area, right? So you need a bunch of particles. It's force per area, so you need a bunch of particles. So oftentimes, the thermodynamic quantities require, in fact, large numbers. All right, so this is one thing. So what about this uncertainty? Well, with the advent of quantum mechanics, we know that it's not an unreasonable assumption to assume that there's uncertainty here. In fact, this is built into the theory of quantum mechanics. But let me purport that actually, even before quantum mechanics, we knew that there was uncertainty, and this is justified by so-called chaos theory, because chaos theory tells us that if we know the situation right now, then just in a few minutes or a few days later, that situation is essentially independent from this situation, and the situation a few days ago is also independent of this situation. So both the future and the past are for all means and purposes independent of the present. And this sort of uncertainty is quite a bit different than the uncertainty that we get from quantum mechanics. For example, in quantum mechanics, we still have the Schrodinger equation. So if you have the wave function, at least you can deterministically say where the wave function is at some point, albeit there's randomness whenever you measure, when you make a measurement. So that it's a different type of randomness. So the randomness that I want to talk about today is the randomness that's developed from chaotic behavior. Okay? It's different because chaotic behavior gives us a sense of independence. And independence does not arise from quantum mechanics alone. Okay? So this is really, I'm justifying statistical mechanics by saying that you can't just assume quantum mechanics and just have the randomness there. You really do need another theory of large particles that provides some sort of independent structure. Okay? And so the randomness provided by chaos is the randomness that allows us to prove so-called ergodicity and also so-called the distributional behavior of the fluctuations, which is exactly the central limit theorem or the stable limit theorems. Okay? So this sort of stuff cannot be proved by quantum mechanics alone. All right. So let me describe a little bit now what chaos, a little bit more about chaos here, what that is. I guess I should describe also what ergodicity is. Okay, so this is my last, perhaps heavy mathematical slide. And so if we have a sequence of random variables, we call them stationary if you take any finite number of them and you shift them, and this distribution is the same as this distribution. Okay? So you take any finite number, if you shift it in time, then the distribution has not changed. That's called a stationary sequence. Okay? So if we have a stationary sequence of random variables, then it's always produced by a measure-preserving map. Okay? So what is a measure-preserving map? A measure-preserving map is any map F such that when we take a measurable set and we look at the pullback of that set, then the probability of that set is the same as the probability of that. So in other words, applying F to a set does not change its probability. And of course, if you apply it again, then it doesn't change. Well, okay, sorry. That's false. It's important to look at the pullback and not the push forward. So if you pull back a set, that doesn't change the probability. On the other hand, it can change the probability if you push it forward. All right? So it's very important to look at the pullback of the set. And so when we look at the pullback, the measure of this is equal to the measure of the original set. And so that's what a measure-preserving map is. We'll see an example in just a second. So now a stationary, what I said right before that is that a stationary sequence always has the form that the nth random variable is exactly just the composition of x and this measure-preserving map composed n times. All right? So this is the construction of any stationary sequence. We can always find some f that does this. And the invariant sigma field under this measure-preserving map is a set of all elements in our sigma field such that they remain invariant under f, under this pullback. Okay? So not only does so the measure preserving map says that we don't change the measure when we pull it back. Here, we don't change it at all. It just stays there. Okay? So it's not just the measure is the same, but B stays the same up to a set of measure 0. Okay? So in measure theory, we always do things up to a set of measure 0. And so we call a map ergodic if the set of all guys in this invariant sigma field is trivial. So the only things that don't change are the whole set and the empty set. Everything else changes somehow in a non-trivial way. Okay? So that's what an invariant, that's what an ergodic map is. It's not so important, but since I am going to use ergodicity throughout the rest of the talk, I guess it's nice to at least know what it is technically. So this is a technical definition. It's not so important to know. If you want, you can replace ergodicity by IID. IID is always ergodic. It's a bit stronger than ergodic, but if this was a little bit too much for you, just think from now on, I'm just going to think of IID sequences. And that will get you through the rest of the talk. Okay? All right. So here's now a measure preserving map. So here's a billiard system. We have a certain table, and then we put a ball on it, which represents a particle, and it just moves and it hits the walls. Okay? So I start off at position X under one iteration of my measure preserving map F. I go to here. Under 2, I go here, etc., and then it just bounces around. And I use that the angle of incidence is the angle of reflection. Okay? So this is just Hamiltonian mechanics. And in order to describe the position of the ball when it hits the walls, I only need 2 things. I need to know where it hit and the angle at which it hit. And once I know those 2 things, I know exactly the next position under Hamiltonian mechanics. And I can know, once I know that, I know also the angle that it will reflect at. And so I can know the next one, et cetera, et cetera. So here, this is what's called a dynamical system. F is called your measure preserving transformation or measure preserving map. And the set of points on which F acts on is called the phase space. So here, the phase space, I'm going to denote the little x's by their position on the boundary of our table, along with the angle at which the ball bounces when it hits that point. Okay? So this is the phase space. And now I'm going to slowly shift from probability language, which I use omega as my sample space, to M, which is the set of all x's. So here, the set of all x's, I have on here this r-axis, the location at which it hits on the boundary, and then here, the angle at which it hits away from the normal. Okay, so here's the normal, and I look at phi away from the normal. So it can either hit all the way this way or all the way that way. So minus pi over 2 to pi over 2. Okay, and F preserves the actually the Lebesgue measure on this, which is just the Liouville measure on this space. Okay, Liouville measure from Hamiltonian dynamics. All right, so that's the setup, and maybe just the important thing is to remember the picture. We're just going from point to point along the boundary of some billiard table according to Hamiltonian dynamics. Okay, so what is chaotic behavior? Well, if I start here, look at my trajectory, then if I just change it just a tiny bit, notice that the result after a few times is completely different. So small changes result in big changes after just a few iterations. And this is the basic principle behind chaotic behavior, chaos. And this is summed up in an object called the Lyapunov exponent. So if we have a small change, so here this is, say, my position, my small change at time 0, so delta x. So we have a small change at time 0. So here, actually, this is just a change in the angle. Then at time t, the change is very big. It actually grows exponentially. Okay, so if we have t equals 10 here, e to the, let's say lambda is 2 and t is 10, then e to the 20 times that change is actually what we see in the change after time equals 10. Okay, so this grows exponentially big. So so why does this result in essentially independent behavior? So chaos, as I said before, gives us essentially independent behavior of the present from the future and a present from the past. So let me give an example. Suppose that we just have numbers that differ by 10 to the minus 16th. So this is the double precision of modern day computers. They only know numbers up to the 10 to the minus 16th digit. So at that point, you don't have any more space to store. And if we have a difference of that much, actually at time 37, if we iterate something, then the difference here becomes order 1. All right? So you've changed a number just because of the accuracy of your computer by iterating something 37 times. And so when we have a positive Lyapunov exponent, we have a positive lambda here. At time 37, we have a very small change affected us at a very large order, of constant order. On the other hand, the negative exponents tell us that the present, if we have just a small change of 10 to the minus 16th, that actually came from, or resulted, if we go backwards in time, of constant order at time negative 37. So we kind of move forward in time, and we also think of moving backward in time. And because of both positive and negative Lyapunov exponents, we get chaos. And in fact, that's one definition of chaos, actually. So this is called a hyperbolic dynamical system because it has both positive and negative Lyapunov exponents. And whenever you have hyperbolic dynamical systems, you have what's called chaos. Both the past and the present are, the past and the future are essentially independent of the present. That's the idea. All right, so chaos actually is not that old. It's younger than dynamical systems and probability as a real, true mathematical field. It started in about it started in 1961 by Edward Lorenz, who was a climate scientist at MIT. And he had some input where he was trying to predict weather patterns. And he put in 0.506, and he noticed that when you change it just a tiny bit, the weather, after just a few days, behaves drastically different. So you can see here in the beginning, it's kind of the same, but then after a while, the simulations completely diverged. All right? And actually, this picture arose because actually, at the time, they were recording data by hand. And so they didn't record, all the decimal places, and they only recorded 3 decimal places. But it turned out that the original data here was 0.506127, and so he wanted to check what went wrong. And when he finally figured it out, he realized, it's because they rounded off to the 3rd decimal place. And if they actually added this, then it gives us a different path. I don't know which path is which, but these are the 2 paths, okay? This is a now famous picture. And this is actually the picture that's behind the so-called butterfly effect. If a butterfly flaps its wings in Japan, a small change can result in a huge change, can cause a tornado in Kansas, right? So that's the butterfly effect. And that's kind of what I was showing you on the previous slide, also with billiards. So that's chaos, and the notion that the future and both the future and the past are independent from the present. All right, so now I finally get to the model that I was studying, which is a certain type of Sinai billiard. So hopefully now you know what I might mean by the billiard system. And this is a type of billiard table that I actually looked at. It's one with a very long cusp, okay? And in the title, I said a cusp with a flat point. It's because that if you look at this, it looks local. What we did is we created a cusp so that it looks locally like y equals x to the r to the beta, where beta is between 2 and infinity. Okay, so like think of a quartic, or and so here the second derivative is actually 0, right? The first derivative is beta minus 1, second derivative is beta minus 2. You put in 0, and if you think of this as the origin, then the second derivative is 0 at the top and also at the bottom. So this is plus y equals x to the 4th. This is minus y equals minus x to the 4th. And they both have second derivative here, and that's what we call a flat point. And this sort of thing changes the behavior of so-called Sinai billiards. So maybe I should describe a bit what Sinai billiards are. But let me make one final comment about our model. So as we know, the ball moves around. and it hits. And the other thing that we're going to do is now we want to sum up something. So what is it that we're going to sum up? Well, what I do is I pretend that this is a pinball table. Hopefully you guys have all played pinball, where you go, you hit the sides and you try to get the ball from going down. And every time you hit something, you get a score. So this is the model. So every time you hit a side, you get a score. Sometimes it's positive, sometimes it's negative, but there's a set price at each point. There's a set cost, or prize. Okay? So here I get 50, here maybe I get 20, here I get negative 10, something like that. So here I have a pinball machine, and you can think of this maybe even as if I'm in a room and I have heaters on one side and I have coolers on another side, and the particle comes along and sometimes it gains heat, sometimes it loses heat. Okay? All right. So that's the model. And what we found when we create a cusp like this is that when we look at a particle and look at the time it spends in a cusp, when a trajectory goes almost along this straight line and it goes in here, it kind of gets stuck. It kind of goes in, and it goes in, it goes in, it goes in, and it just goes further and further in, and it gets really hard to come out. And eventually, at the very end, the angle starts relaxing a little bit, and then you go like this, and then eventually it comes back out. Okay, so that's the picture. So we have the ball coming into the cusp, and when it goes in at a thin enough angle, it gets stuck there for a very long time, and so we get power law return times to here, what I call the east side. So let's call these three walls the east side. Okay, so if you start here, you go in, every once in a while you get stuck there, and the power law time, this 1 over alpha, the alpha is related to the actual curvature of these walls here. So actually the curvature is 0, but you know what I mean, the shape. Okay, the shape of the walls there. And if the shape has this beta bigger than 2, then notice that this is between 1 and 2 for all beta between 2 and infinity. All right? So this is the cusp, and this is the model that we studied. And this is what we showed. So F is a score that you get each time you hit a wall. And we now move along with this capital F, which moves you to the next point. So you get another score. So this is the first score that you get, second score, third score, fourth score, whatever. And now, if you sum these up, then when you normalize, and we'll assume that the pinball scores have an average of 0, so mean 0. This all it's saying is mean 0 on the boundary, or on the space M, with the space of all the phase space of all r and also angles. Okay, so we have some measure there. Then when we divide by n to the 1 over alpha, we converge to a stable law. And our alpha is given exactly by the shape of only the cusp. So that the cusp completely determines the limit law. The shape of the rest of the billiard table doesn't matter. It's just how thin that cusp is. And here we also computed sigma, but you can barely see it. And I did that on purpose because sigma here is not important. Don't look at this and try to figure out what sigma is. The point is, here we got a stable law, and we figured out that the alpha of the stable law corresponds exactly to the thinness of this cusp. All right. So we sent it in for publication. I don't know when this is probably going to be more like 2018 or 19, the way math papers go, right? So, okay. So why do we get the stable law? Or so how do we get the stable law? So I'm going to now give you the ideas of the proof. This is the last mathematical portion. So the ideas of the proof is that first we remove the cusp, and we kind of look at some reduced space. Okay, so here I'm going to call non-script m, just the text m, this spot. And so I've removed the cusp because this is where the singular behavior occurs. But if you think about it, if we have a continuous function, so notice in the previous slide I should have actually said also that f is Holder continuous. So it has nice continuity properties, the scores. So the scores don't change so much when we move around the boundary. But if we're Holder continuous, then essentially it looks like a constant near the tip of the cusp. So when we go in there, we're getting the same score over and over and over if we get stuck in there. And that's exactly this picture, right? We're adding 1, 1, 1, 1, 1. Actually, it's f of the cusp, f of the cusp, f of the cusp, over and over and over for a very long time. Exactly n to the alpha time, right? okay, well actually it's here, n to the 1 over alpha time. You add that anytime you get stuck into the cusp. Okay, so that's the picture. And so when you chop this off and you add this this many times, you get this sort of behavior. And that was just like adding the tau i's from before in our on-off model. And now the second thing we do is now we look at this reduced space. We just look at this and think of now that as our conditional probability space. Okay? So everyone knows about conditional probability. So here I chop it off and I consider now a reduced space and I look at the conditional measure there. And now but the thing is every once in a while I get pushed in here. So I have to change my dynamical system a little bit. And so what I do is I just take my map F and I iterate it r times. So r times is the return time. How many times do I hit this cusp before moving back to the east side? So if I get here 10 times, then r is equal to 10. And now t is just f to the r. So it's a random time. It's random depending on the point at which I left and the angle at which I left. But it's a time nonetheless. And so this is sort of a random composition of this guy. Okay, so that's my new dynamical system. And the next step is just to show that this dynamical system actually has exponential decay of correlations, which for all intents and purposes means it's independent. So you have IID random variables on this conditioned space. The next step is to show that the return time has power law decay. That's exactly that the return time is of order n to the 1 over alpha. Right? R greater than c times n to the 1 over alpha. That was kind of the thing that gave us the power, the stable limit theorem. Right? That's what I described in the beginning. So if I have power law return times and decay of correlation which gives me independence, then I've essentially shown you, that was my first part of the talk, that you get a stable limit. That's the alpha stable limit theorem. So here I don't have independence, but I have strong enough decay of correlation. And so what I can use is the so-called Bernstein block method, or the Bernstein little block, big block method, as it's called in Resnick's book. And then finally, I have to now, what I did now is just looked at the return times, but now I want to generalize. So the return times would work, this would prove the theorem if I only had 1 on the cusp and say 0 elsewhere, and then I normalized and made it mean 0. So then the return time would exactly be my score. Anytime I go into the cusp, I add 1, 1, 1, 1, 1, 1. And when I come out, the return time is my function. But if I want to generalize, then I use some other Holder continuous function. Then I have to add this Holder continuous function r times. And if it's continuous enough, then we essentially, you think of this as constant. When we get, for very large values of r, when it gets stuck into the cusp, it's essentially constant. Okay, so that's the idea. So we generalize to these induced functions, not just the return time function. And then finally, we extend to the original map by some continuity argument, okay, which is called the continuous mapping theorem. I guess I should point out that I pointed out to you earlier that the processes that we get here, the alpha stable Levy process, are actually not continuous. So you might be thinking, well, how do I use continuity here? Well, it's not continuity of the process. It's actually continuity of the space in which the process lives. And the space in which the process lives are the right continuous left limit functions. The right continuous left limit paths, which are the so-called Cadillac paths. And they have a topology on them called the Skorodd topology. And so if you look at the Skorodd topology, if you take the path and you change the time a little bit, then the projection back to the Skorodd space is continuous. So it's a little bit complicated. So I'm not going to talk about this too much. I mean, I think I probably lost you in that last couple sentences. So don't worry too much about that. But hopefully you got the basic idea. So let me kind of review. You just have to obtain power law return times. You go into the cusp and make sure that this is of order n to the 1 over alpha time that you spend in there. You get decay of correlations, which tells us it's essentially independent. You use those two things, and Bernstein block method allows us to upgrade decay of correlations to essentially independence. So now I have independence, power law return times, and then I get convergence to the Poisson. And remember, the Poisson builds up the stable law. And then finally, I have to do some technical stuff here. Okay, so this is technical stuff. And this is somewhat technical to get the actual decay of correlations. So let me just focus in on these two things. Now, actually, this is quite technical as well. This required 5 pages of calculations in our paper, which also relied on 7 pages of calculations in another paper. So altogether, it was 12 pages of calculations. So it's quite technical. But here's a lesson for the graduate students. Whenever you have, how does someone figure out, oh, I'm going to get this at the end. I'm just going to do my 12 pages of calculations, and I know what the end is. Well, there's always some intuition, some picture in the back of your mind that guides you along those calculations. And this is the way that your thesis is going to eventually be written. Okay, so you have some guiding picture, and then you do the calculations. And here's our guiding picture. Okay, so I'm not going to give you the 5 pages of calculations we did, but here's the guiding picture. Well, here's a ball, and we change the angle just a tiny bit. And what happens is, if we change the angle just a tiny bit, some of the guys land here, but other of the guys move past the obstacle in the middle and land here. Right? And so you see that they get split up. If you just change just a tiny bit the angle, sometimes you hit one wall, sometimes you hit another wall. And so it splits up the space M. So this is a space M, and we split it up. And there are these singular lines. Whenever the angle that gets changed just a tiny bit splits up our path space. And this is actually the source of chaotic behavior, right? If we split things up enough, then they just end up going all over the place. So now here, this is the picture. And so what we've done is we've split up kind of our space M. So this is our space M R down here, and angle phi from minus pi to pi over 2, minus pi over 2 to pi over 2. And you just split this up, and you have to calculate what is the area here. That's the measure, or that's the probability of the return time. So this is all the set of points that return, say, after 100 points, going into the cusp and come back after 100. And that, if you go one step further, that's 101 times in the cusp. And then 102 times. And as you go towards it, closer and closer to this wall, this line here, it's going towards off to infinity. You get stuck further and further in. So 1,000 times in there, 1,000,000 times in there. And so you have to calculate what this guy is. Well, it's impossible to calculate this, sort of. But what we do is actually, now we expand the picture. We look actually in the cusp. So this is the picture in the cusp. So here, I've kind of drawn the line where I've chopped off this cusp. And so now I look at this is the induced space after I chopped off the space, the conditional space. And so now I look back at the original space, and I go in, and I calculate how much. So this is, I move from here to here to here to here to here. This is actually my ball bouncing back and forth. And it's impossible to calculate the area, but as I get further and further in, I can calculate better and better, because actually the limit is getting flatter and flatter, and it actually goes towards pi over 2, which is when the ball is actually just stuck between 2 parallel lines. So the limit looks like that. So as I get closer and closer, I can actually calculate this, and I can count how many times it goes here. And then that gives me information to what this area is. And as I get closer and closer to here, this looks more and more like a rectangle. And once I know that it looks more and more like a rectangle, all I need to do is multiply the length of that times the height of that. And in the limit, this all works. So you have to kind of figure out what the asymptotics are. So it's all about figuring out those asymptotics. So that's the picture that gives us the power law return times. Okay? All right, so I'm almost done. So this is the other thing that I said I would discuss, which is Bernstein's block method. How do we go from exponential decay of correlations up to independence? And now, for those of you, I know I see many people from my 550 class. This was actually section 8.6.1. I skipped it. I skipped this section. We're in chapter 10 now, but I skipped this section. But here, this is actually a picture I took from his book. This is our book, right? And so if you want to know this in detail, go back and look at section 8.6.1 about M-dependent central limit theorems, okay? So let me explain the picture. So what I do is, if I add a bunch of random variables, n random variables, and suppose many of them, so let's say the probability of these are being 1 is 1 over n, and the probability of these being 0 is, again, 1 minus 1 over n. So that the sum converges to Poisson, right? If they were IID. But they're not IID. So the probability that this is 1 over n can affect the probability that this is 1 over n, can affect the probability that this is 1 over n. So we don't have independence. But what we do is, if what we do is we split this into big blocks and small blocks. Big block, small block, big block, small block. And the big blocks are of order bigger than the small blocks. So here, n to the b is of order bigger than n to the a, but smaller than the total number of blocks. Okay? And now, what is the total number of ones that we can get from all the small blocks? Well, the small blocks are of smaller order than the big blocks, so there are exactly n, oh, well, not exactly, but of order n to the b minus 1 big blocks. The big blocks dominate how many blocks there are. Okay? So think like big blocks could be of size square root of n, small blocks could be size cube root of n. So if we have square root of n plus cube root of n, that's still of order square root of n. And if I have n blocks, then there are square root of n. If I have n total guys, then there are still of order square root of n big blocks. So that dominates how many big blocks, how many blocks there are in general. And so at most we could have a times n to the a times n to the b minus 1, which is of order less than n. So if we sum all the possible ones over all the small blocks, in the end they're negligible. Right? So we can just throw away the small blocks. So, but the small blocks serve the purpose of separating the big blocks. So they're growing. The separation is growing and growing and growing. And if I have exponential decay between the two guys, then as they grow further and further and further, they become more and more independent. And if it's exponential decay, we look at the characteristic function, and we know that the characteristic function has a natural exponential in there. And so when we have exponential decay, the order at which it affects the independence is small enough to throw away, so we essentially get independence. Okay? So that's kind of the idea. So if you want the technical details, go and read the book. But here, we just now have to sum over the big blocks. All the possible ones in the big blocks. That's of order n to the b times n to the b minus 1, which is of order, there are of order n guys in all the big blocks. Now, there's one technicality left, is we actually have to show, what about within a big block? Within a big block, they're still dependent. So somehow you have to show that that converges to Poisson. And so there are two types of decay of correlation that one needs to prove when you are doing this big block, small block method, which is an exponential decay across all n, and locally you need some fast decay of the pairwise correlations. And so that's all I want to say about that. So let me end finally with one question. There are many questions that I could ask, but this is the one that I think is my favorite next open question in this. Okay? So I analyzed one particle, and in general, ergodicity and central limit theorem, if you don't have a cusp, central limit theorem has been proved by Sinai and his students. But if you do have a cusp, now we've proved that you have a stable law, but and the stable law essentially arose because these guys are highly correlated, right? When you're inside, if you get a score that's close to the cusp, the next score is also close to the cusp. So they're highly correlated for a very long time. So we have exponential decay at this scale, but high correlations at this scale, and that's how we got stable law behavior. However, if we now, instead of take this n limit, but let's take the user limit. Let's say we have many, many students. Some of them are on, some of them are off. Some of them are on, some of them are off. If they randomly are on and off the computers, if we take the limit in number of students first, then ones and zeros will give us a Gaussian number of people being on or off after we centralize at any fixed time. So we fix the time. We don't take time to infinity. We fix the time. We take the number of users to infinity, and you get a Gaussian. But the correlation remains. And it's well known that if you have Gaussians that are correlated in a certain way, when you sum them up and normalize in a proper way, you get fractional Brownian motion. Okay, so here, if we take the number of users, if we take the number of balls to infinity first, and then take the limit as they are bouncing around, then my conjecture is that that sum converges to fractional Brownian motion. It's not a wild conjecture. Actually, this is also based off of a paper of Resnick and Mikosh and a couple other co-authors where they actually proved it in a slightly simpler model. They showed that if you do the limits in a certain way, you get an alpha stable law, but if you switch the limits, you actually get a fractional Brownian motion. So my conjecture is that this would also hold in this situation. And so with that, let me conclude my talk. Here are some references.